Algebra 2, Chapter 11, Section 2, Solving Exponential Equations Using Logarithms. Let's apply what we learned in 11.1 to some examples of how to solve general exponential equations. We can solve an exponential equation using the technique of taking the logarithm of both sides. Here's an example. Solve 3 to the t is 4,000. So we saw an example earlier where we had 10 to the t is 4,000. But now we're saying solve 3 to the t is 4,000. So we can do this by taking the log of both sides of the equation. And of course the caveat here being that both sides have to be positive, or we have an issue here where it's not equivalent. So we could introduce extraneous solutions here, and we could also not get us the answer if we have a negative. We could get the wrong answer. So be careful of the domain of the logarithm when we take the log of both sides. In this case, an exponential is always positive, 4,000 is positive, we're good. We can pull t out in front using the rules of logs. Log of 3 is a number, log of 4,000 is a number. We can write log of 4,000 divided by log of 3 by dividing both sides by log of 3, and that's our answer. So we can grab our calculator and write log of 4,000 divided by log of 3, and we get 7.550, rounding to the nearest thousandth of a digit. And if we round it to the nearest, let's round to the nearest 10,000th, 7.5496. 7.5496. And that's our good enough solution for this problem. Suppose $4,000 is invested in a fund that doubles every 12 years. When will the fund balance be $7,000? So here's an expression representing the fund's balance at any point in time. 4,000 is what we invest. 2 is the doubling factor. T divided by 12 means that it doubles every 12 years. Then we want to know when is the output of that 7,000. So we need to solve for t. T is in the exponent, so we'll need to use our exponential solving techniques by taking the logarithm of both sides. But before we take the logarithm of both sides, let's divide both sides by 4,000. So we get 7/4 on the right, since the thousands cancel. Now taking the logarithm of both sides, we have log of 2 to the t over 12 is the log of 7/4. And now we can pull the exponent down in front by the rules of logarithms, which gives us t over 12 times the log of 2. Remember, the log of 2 is a number. And that equals the log of 7/4, also a number. We can rewrite this as t over 12 is log 7/4 over log 2. And multiplying both sides by 12, we get t is 12 log 7/4 over log 2. So pull up our calculator, and we can evaluate the logarithms in order to get a rough answer. We have log of 7/4 divided by log of 2 times 12. 9.6883. .6883 is roughly the answer. Let's solve this equation. 5 times 7 to the x is 20 in two different ways. First, divide by 5 and then solve. Okay, so 7 to the x is 20 divided by 5, which is 4. Solving by taking the log of both sides, we would have log 7 to the x is log 4. Using the rules of logarithms, we can pull the x in front. X log 7 is log 4. And we get x is log 4 over log 7, which is approximately, let's grab our calculator, log 4 over log 7, 0.7124. 0.71241, we'll say 0.71241. B, solve by taking the logarithm of both sides first. So log of 5 times 7 to the x is log of 20. Now we can't pull the exponent down in front yet. It's not because it's not an exponent for both of these numbers. Okay, that was only if we had a number to an exponent. It is not true that x log 5 times 7 is equal to log 5 times 7 to the x. What we can do is use the multiplication rule and break this into two addition of logs. Log of 5 plus the log of 7 to the x is log of 20. Now we can subtract log 5, and we can pull the x in front now that it's just on one expression. X log 7 is log 20 minus log 5, and then divide both sides by log 7. Log 7, of course log 7 over log 7 is 1, so x would be log 20 minus log 5, log of 20 minus log of 5 divided by log of 7. And that gives us 0.71241. 0.71241. Sure enough, same answer, even though these look different. Now we could use the rules of logarithms to combine this into log 4 and see why this is the same. Remember, if we're subtracting two logs, we can divide the two numbers in one logarithm. And of course 20 over 5 is 4. And so now you can see analytically these are the same number, log of 4 over log of 7. Let's solve 300 times 7x to the 45. I think it's much easier to divide by the 300 first, so we only have one set of logarithms to deal with. So we have log 7 to the x is log of 45 over 300. And we can pull the x in front, divide both sides by log 7. We get log 45 over 300 all over log of 7 is our answer to this equation. So we can take the log of 45 over 300. Be sure we do 45 over 300 first. By putting it in parentheses, we get a number. Notice it's negative. It's negative because the input was less than 1. Which means that we have a negative exponent of 10 to get such a number. Divide by log of 7, and we get negative 0.9749. Negative 0.9749. And that makes sense because we're saying here that the exponential growth is really decay. This is a growth factor of 7. This is a huge growth. We're asking when is it smaller than the initial value, so this should be a negative number. Negative 0.9749. John invests $2,500 at 4.4% in a retirement fund that has no fees. Katie invests also $2,500 at a higher interest rate, 5.1%. But in order to get that better interest rate, she had to pay an upfront fee of $1,300 as a setup fee for her initial balance. When do their investments have the same value, and who made the better choice? So we need to model each of these. So John's balance is going to be $2,500. We need to turn this into an annual growth factor. So 1.044 by turning the percent into a decimal and adding 1 to go from a rate to a factor. 1.044 to the time power t. And Katie's balance is she starts with $2,500 minus her $1,300 fee to 1.051 to the t, which 2,500 minus 1,300 is 1,200, 1.057 to the t. When do they have the same value? Well, we now need to write an equation by setting John and Katie's balances equal to each other, solving for t. Now, until just now, we would have to guess and check to do this, but we can now take the logarithm of both sides in order to solve. Now, there are two techniques again. We can take the logarithm immediately, or we can try to combine things such that we have less logarithms. I'm going to do it both ways. so that we can get practice both ways. So if we take the logarithm immediately, we have the problem that we can't just pull t, the exponent, out in front because it's not on the whole inside part of the logarithm. What we have to do is use the multiplication rule for logarithms to turn the multiplication into addition, and then rearrange it the algebra we already know. Log 2500 plus, and I'm going to go ahead and pull the t in front now that I can. T log 1.044 is log 1200 plus t log 1.057. Now we need to get the t's on one side and the not t's on the other side. So subtracting log of 1200, log 2500 minus log 1200 equals t. So now we need to move t log 1.044 to the right hand side, so we'll subtract it. T log 1.057 minus t log 1.044. Combining the t's here so we can factor t out of both of these, and I'm going to do this all kind of right here so I'm running out of space. If we can factor the t out, we have t times log of 1.057 minus log of 1.044, and now we can divide both sides of the equation by this value, which essentially moves it under here. So to evaluate what t is, we need to take log of 2500, subtract the log of 1200, divide that all by the log of 1.057 minus the log of 1.044, and we get 59.31. So I noticed here we have a mistake. Sorry, there's a issue here with the rate. I thought this was a 7. I got sloppy. Remember, Katie's rate was 5.1%. This is a 1, not a 7. Sorry if you're wondering about that. That was a mistake. So let's erase all these 7s and replace them with 1s. So really it was 5.1%. So let's go back to the calculator and do this again. So we have log 2500, that didn't change, minus log 1200 divided by the log of 1.051 minus the log of 1.044. And that's 109.83. 109.83 years. Okay, so you can see it takes a long time for these to have the same balance. So that was doing it the way of taking logs first. Let's try over here rearranging first. So rearranging first, let's divide by 1200 on both sides first, and the zeros go away. 2500 over 1200 is just 25/12, same fraction. And then we have 1.051 to the t over 1.044 to the t. This is the same exponent, so we can actually put the parentheses around the division and do the division first. 1.051 over 1.044 to the t. Now if we take the logarithm of both sides, this is a little simpler. We have log 25/12 is t, pulling it down in front while I'm doing this, t log of 1.051 over 1.044, and then we can divide both sides by log 1.051 over 1.044 and get the answer. So that would be log of 25/12 over the log of 1.051 over 1.044 gives us 109.83 years. So of course we get the same answer since they're equivalent ways of working the problem. And I feel like the second way is much simpler, so I would suggest trying to rearrange the equation into this form before you take the logarithm of both sides to simplify your work. Who made the better investment choice? Well, John did. He is presumably going to retire in less than 109 years from now. He'll have more money in his account. While Katie had a higher rate, it's just not a high enough rate to justify this huge initial expense, unless somehow she was planning on investing the money longer than 109 years. So this is a good kind of exercise to do. There's all kinds of investment strategies where you have to pay up front some fee. or pay a periodic fee. It's helpful to know how to analyze these kinds of problems. To solve logarithmic equations, take 10 to the power of each side. So now that we've studied logarithms, we can write an equation in logarithm form that we need to solve. We need to solve for n. The log of n is 1.9294. So if we take 10 to the both sides, we get 10 to the log n. So we put log n inside the exponent of 10 to the power is 10 to the 1.9294. And again, don't forget to go back and check if you get a negative or 0 n, this isn't going to be a real solution. 10 to the log of n is just n, as long as n is positive, like I just said. So we have 10 to the 1.9294 power, which we can find on our calculator. 10 to the 1.9294 is 84.996. We're just going to call that 85. N is 85. Solve 4 times the log of 2x minus 6 equals 8. Again, we could just take 10 to the power of 10 to the both sides, but it's going to be extra complicated. Let's take care of this 4 first. If we divide both sides by 4, we just have log of 2x minus 6 is 2. And now when we take 10 to the both sides, we have 10 to the log of 2x minus 6 equals 10 squared, which gives 10 to the log of this is just that, 2x minus 6. 10 squared is 100. Adding 6 to both sides gives us 106. X is 106 divided by 2, which would be 53. That's our answer. And since the answer is positive, we're fine. Well, the logarithm itself needs to be positive. So 2 times 53 is 106 minus 6. 100. The inside of the logarithm is 100. That's positive, so we didn't get a wrong answer. Solve log of x plus 198 minus 2 is log of x. Well, here we at first might not think we can do a lot to help with the 10 to the power, but we really can make this simpler by first manipulating to get all the logarithms on one side. Log of x plus 198 minus log of x is 2. Moving the 2 over and the log of x over. And now remember the rule, if we're subtracting logs, we can divide the two numbers inside the logs, put that in one logarithm. As long as x isn't 0, we can do this, which if x is 0, the logarithm is also not defined, so that's okay. Now we take 10 to the power of both sides, we get 10 to the log, which is going to make that go away. So we'd have x plus 198 over x is 10 to the 2, or 10 squared is 100. Multiplying both sides by x, x plus 198 is 100x. Subtract x from the left to the right. 99x, x would be 2. And 2 is positive, so log of 2 is defined. 2 plus 198 is 200. That's defined. This is an answer. Solve log of x plus log of x minus 3 is 1. So let's use the property of logarithms to make this one log. Addition becomes multiplication, so multiply the insides. Take 10 to the power of both sides, so you have 10 to the log of this equals 10 to the first. 10 to the log is just the thing inside of it. It's an identity. 10 to the first is 10. X, now we need to distribute. We get x squared minus 3x minus 10 is 0. We have a lot of ways we could solve this equation. We could use the quadratic equation. We could factor. So we could try factoring real quick. This looks like it might factor. Two things that multiply to minus 10 could be 5 and negative 5 and 2, and that adds to negative 3. So x minus 5 times x plus 2 would give us minus 3x and negative 10. And so the answers would be x could be 5 and x could be negative 2. But let's go back and check. If x is 5, we have positive 5 minus 3 is 2 positive. If x is negative 2, it's no good because we have log of negative, which is undefined. So we actually have one answer. X is 5.